let's start by taking a look at assigning oxidation numbers. We can't spend too much time on this. Let's see. So, yeah, the general way you do this. So oxidation numbers. Remember when we would whenever you learn about ionic nomenclature and that kind of stuff, we're referring to in a really simple case. When you're thinking about a really simple case, for example, if you had something like sodium chloride, we would say the oxidation state on chloride is -1, and the oxidation number for sodium is plus. And then the cases can get a little bit more complicated when you're dealing with things like iron. So, for example, iron has multiple oxidation states. And so, for example, in this first iron compound on the left here, we deduce that iron must be +2 because chloride is -1. So if we know that chloride is -1, then we know that this whole chunk here is -2. And so this thing has to be electrically neutral. So it comes out to be +2. But if we look over here, right, if this is -1, well, now I have 3 of these. So that implies that this is going to be +3. We take it a little bit further in this chapter by looking at, I guess in finer detail at the different oxidation states in some cases. So in previous, when we're learning nomenclature, for example, and we look at this, typically we call the sulfate anion -2, so we would know that iron is +2, and we would sort of, this whole polyatomic ion, we would just call -2. And that's still true, but now we can go in and assign individual oxidation states to the sulfur, for example, and the oxygen atoms. And so the way that we do that is just that oxygen, should I put this, maybe I'll put it off to the side up here. Oxygen is -2. Let's see, the exception, because of course there's an exception because it's chemistry, is in peroxides. So peroxides are when you have 2 oxygens that are directly bonded to one another. So for example, in hydrogen peroxide, which looks like this, the oxygens have a -1 charge, but generally speaking, it's a -2. So outside of peroxide, you'd see this probably more typically, at least in this class, written as this. In that case, it's -1. And then the other thing that helps us is that hydrogen is always +1. The exception is when it's bonded to a metal. So for example, like NaH, that's not going to be +1. There it becomes -1. So there it's a -1. Things that are bonded to themselves do not have oxidation numbers. So for example, I'll just assume like a more technical way to say that is purely covalent bonds have no oxidation state, but things like nitrogen or hydrogen or oxygen, when they're by themselves, these all have 0, like a neutral oxidation number. So that should be, I mean, I guess it's not super obvious because a lot of this is sort of a convention, but like, yeah, nitrogen, hydrogen, oxygen, what's the charge on hydrogen in that? Yeah, it's just 0 on both. You know, what's the charge on oxygen? Which, yeah, again, it's just 0. Same thing for nitrogen. Same thing for nitrogen. But yeah, but we can use these two concepts here to assign more detail on the oxidation states for these types of things. So if we're taking a look at sulfate, for example, let's like speciate it out here. So let's say we're looking at sulfate and we're trying to figure out what the oxidation state is for the sulfur atom. So we know the overall charge on sulfate is -2. And what that means is that the sum of the individual oxidation states on the atoms must add up to -2. And so the only things we know for sure typically are that oxygen is -2, which is what we have here. It's not a peroxide, so we don't have to worry about that. And so that doesn't change. So we know that oxygen has a -2 charge itself. So I'm going to put a bracket around this just to make it clear. The -2 charge is on the overall sulfate. It's not on the individual atom. The individual atom has a -2, which means that the oxygens contribute a total of -8. And that's what tells us that sulfate should be +6. And so that's the kind of math that you end up doing here. The reason, so if you look at, so if you're trying to kind of figure out like what the hell's going on there, if you actually draw out the Lewis structure for it, it looks like this. So what you're really doing, you don't have to do it this way, but just so you can kind of visualize, because this gets a little bit messy if you're not familiar how to do this. What you're really doing is you're going in and you're assigning a charge to an oxidation number to each one of these individual atoms. And so like this has a -1, this has a -1. Yeah, I guess that's one way to look at it. I don't know how helpful that is, but that's what's going on here. That's what's giving you this overall charge here. So this is -1, that's -1, so it adds up to -2. Yeah, actually, I guess that makes that more confusing. Don't worry about formal charges. But yeah, you're talking about these sort of individual atoms in here and their oxidation states. And all we're saying is that the sum of their oxidation states should equal -2. And that's what we see here. We want to know the oxidation state because it's a useful convention, especially when we get into dealing with electrochemistry. We'll see, or even just balancing redox equations, we have to know it. We could get deeper into like what oxidation states mean, but I don't think it ends up not being practically or super pragmatic for problem solving, which is ultimately what you have to use this stuff for. The assumption is that the electrons are, like when you're assigning oxidation states, the assumption is that the electrons are 100%, for example, here are divided. So, the chloride really does have 1 extra electron and the sodium really does have 1 less electron. That's what sort of the oxidation state idea comes from. You pretend as if the bonds are like purely ionic. You can see how this stuff, yeah, it's not that helpful for problem solving. Neutral, these are all neutral just because if you think about an ionic bond, or like if we're talking about ionic bonds, you're talking about differences in electronegativity. And so if you're assuming that something is purely ionic, you're assuming that it has a large difference in electronegativity. The electronegativity difference between an atom, which is exactly the same, is 0, right? So there's no way you could assign a charge here because there's no charge distribution of the electron cloud. But you don't have to get that heady about it. This is, we're just going to solve some problems. We're going to assign oxidation states. We're going to use that for looking at electrochemistry and how batteries work and all this kind of stuff. So anyway, so this let's just try, I'll do one more real quick. Let's see. Yeah, like let's say you're looking at this. We might solve a redox equation involving this. So if you have manganese oxide, manganese has like a million different oxidation states, and it's got a negative on it. So this negative applies to this whole molecule, or this whole compound, or whatever you want to call it. And so we know that the sum of the individual oxidation states, the oxidation state on oxygen and manganese, must sum up to -1. And so all I have to remember is that oxygen is typically -2, and that allows me to set up a pretty straightforward equation. So yeah, so oxygen is going to this is going to have a -2 charge on it. I have 4 of them, so 4 oxygen atoms, each with a -2 charge, means that the charge from the contribution from the oxygen is -8. And so, you just end up with a very straightforward, if you wanted to write it out algebraically, you could say, what -8 gives me -1? X -8 equals -1 or something like that and solve it. But you can do it really by inspection. You're just saying, okay, this is -8. I know whatever I'm adding to it has to equal -1. So yeah, what does this have to be? +7. So you should be able to do this oxidation number assignment stuff super, super fast. Like you don't want to be, you can't afford to kind of struggle with this. This is sort of the starting point for solving, I think, almost every single problem in Unit 4. And it's not like incredibly overwhelmingly challenging, but it's definitely not something you want to be learning the night before. So, and depending on what your high school education was like and who you had for General Chemistry 1, it could take a little while to learn it. So just make some space for that. I'm trying to think if there's anything else. Yeah, nothing else really. I mean, yeah, the exceptions, I guess, just be careful with the the metal hydrides or whatever. Those are the only kind of weird ones. So like if you're looking at like what's a good one that has hydrogen in it? I'm trying to use one that's not yeah, I don't know. Like let's say you're looking at something like this. I'm sorry, I have to draw the structure after this one because I can't think about it any other way. But so like here, what's our hydrogen charge going to be? Well, it's not bonded to a metal. Carbon's not a metal; it's a metalloid. Usually, when you're talking about hydrogen bonded to a metal, you're talking about group 1s like sodium, potassium, lithium. It's not strictly that, but so yeah. So anyway, it's bonded to a carbon. So what's going to be the charge on that? It's going to be +1. This will be +1. We have an oxygen. What's oxygen? It's going to be -2. Yeah, what's the charge going to be on carbon? It's 0. But so those are our oxidation states for this molecule. But if we look at something like lithium hydride, or sodium hydride, potassium hydride, right? In all of these cases, this becomes -1. And so you do see this case up here is a little bit more unusual. When you have peroxide, it's not insane. And you'll see this sometimes. But the metal hydrides pop up a lot because like if you're looking at people don't talk about them as much anymore, but like trying to make hydrogen gas, usually you'll start something in there will have a -1 charge on it. It'll be a hydride or something. So these are reasonably common to pop up. So you're just looking for metals, though. That's what cues you in. This is what cues me in. That's a -1 charge. Let's see. We have this week, next week, which we have Monday of next week, or at least because it's Thanksgiving. Yeah, and then we have one more class, and then we have an exam. So a couple of weeks. So whatever we make it through in terms of electrochemistry will be on that exam, and then we can figure out what to do for the final post. Yeah, the second part of the semester goes by pretty quick. Okay, so anyway, so that's assigning oxidation states, and that's about as tricky as it gets. It does take a little bit of work. All right, let's take a look then at oxidation and reduction. So let's just start by defining what they are. So oxidation, this part can be a little bit confusing. It's not confusing when you think about it, but it can get a little bit confusing when you're trying to think about it quickly. So oxidation is a loss of electrons. And reduction is a gain of electrons. But so a loss of electrons, because electrons are negative, means like increase. I guess it's okay to use that. It's like an increase. I'm going to say gain of positive charge. With that. And a gain of electrons means a loss of positive charge. So for example, if we look at, for example, this really like straightforward reaction. So if you take sodium metal and mix it with chlorine gas, sounds like a really scary reaction. Both of those are pretty dangerous. What you get out of that is going to be sodium chloride. And so this reaction is a redox reaction, which means that it involves, so redox reactions involve not surprisingly, oxidations and reductions. So in a redox reaction, you'll have something getting oxidized and you'll have something getting reduced. And so if we look at this reaction, what's going to be the charge on chlorine? Just 0, because it's bonded to itself or whatever. I'm going to explicitly write out the 0, even though you don't have to. And then what's the charge on sodium? So we're used to thinking of sodium as being +1, but since it's not written out explicitly, that means that it's 0 as well. Right, so if it was +1, which is typically what the state that we find it in, it would be written like this, but it's not. So if you have a metal that's by itself and it has nothing written above it, then it's 0. So for example, if I look at like platinum or something and it's just written like this, that means that its oxidation state is 0. It's just pure platinum metal. Whereas, if I look at it like that, now I have platinum +2. So you just have to pay attention to what it's written as. So when things are just written by them, like when you just have an atom that's written by itself like this, and it's not part of a compound, you just pay attention to what the charge is on it. If nothing's written, it's 0. If something's written on it, it's whatever's written on it, +1, +2, whatever. But so we can come over here on this other side of this equation and look at what's happened here. So the chlorine went from having a 0 charge to a -1 charge. And the sodium went from having a 0 charge to a +1 charge. And so what happened, what happened is we went from here, here, versus here, here. For the sodium, let's see, we have a positive charge. So that means if we come back up here and look, so gain of positive charge, which is what this has, means that we lost electrons. It's an oxidation. So this guy, we'll just call it the oxidation for now. This is our oxidation. And then if we look at the chlorine, right, it picked up an electron. So it went from 0 to a -1. So it loss of a positive charge. You could also call it gain of negative charge, whatever. But it's gaining electrons. So it's becoming more negative. And so that's our reduction. So these things always happen together. It's sort of like I don't want to say it's like acid-base chemistry, but they're oxidation and reduction are like, they happen simultaneously, because you could think about it, if it's sort of like an accounting situation, like, money, if you get money, it has to come from somewhere, like the money doesn't just, well, maybe if you're the federal government, you can just print it out. But generally speaking, like your gain of money, someone else is losing money. And the same thing is true with these oxidation reduction reactions. If this, let's look at the reduction. If this is gaining an electron, if the chlorine is gaining an electron here, that has to come from somewhere. So something else must be getting oxidized. And in this case, it's the sodium. So oxidation and reduction reactions take place simultaneously. So you can't, because you have to pick up electrons from somewhere. Let's see. What are some other things we can say about this? I guess to add to the kind of the confusion of things, just more confusing language, so that the basic concept here, like on a very, very simple level, is that in these reactions, so one of the atoms or one of the compounds or something, I guess one of the atoms is typically going to be losing electrons, and the other atom is going to be picking that electron up. That's it, right? We're talking about atoms just giving up electrons and picking up electrons. So this guy's throwing away an electron and this guy's picking up that electron. That's what an oxidation reduction reaction is. Attached to that is all this kind of confusing ass language. So loss of electron means gain of positive charge, gain of electron means loss of positive charge. But if you sit down and kind of think about what's going on there, it makes sense. It just takes a while to get used to talking about it in a way that it doesn't feel confusing. So, but yeah, so here's some more confusing language. Not my fault. This is just the way the subject is. The species that is being oxidized is the reducing agent. The species being reduced is the oxidizing agent. So we have this concept of reducing agent and oxidizing agent. If we come back up here and look at this reaction that we're looking at, so here the sodium is being oxidized, which means that it is the reducing agent. The reason that we use this language is because it's sort of like if you think about the chlorine in isolation and you're saying, okay, I want to reduce chlorine. Right, I want to perform this reaction where I reduce this. I need something that can do that for me because, as I stated earlier, you can't just pull electrons out of thin air. They have to come from somewhere. And so the sodium is where the electron comes from. So it's the agent that does the reduction. So this, if you take chlorine and you want to reduce it, you can put sodium into the flask with it and it will reduce it. So this is a reducing agent in the sense that it can cause a reduction in another molecule. And the corollary to that holds as well, which is that if we want to oxidize sodium, for example, we have to add something to the flask to oxidize it. Something has to take the electron away. And in that sense, the chlorine is the oxidizing agent. So I add this in, it takes the electron away. It's the agent that performs the oxidation. So that's where this language all comes from. So we have oxidation, which is the loss of electrons, which is a gain of positive charge. And the thing being oxidized is a reducing agent. So you can see that it takes a little bit of time to kind of master the language behind all this stuff. So make sure to spend a little bit of time thinking about that. So yeah, so this is a pretty simple reaction here. We can look at something where it looks a little bit wonkier. So let's take methane. So this is a super common reaction. We take methane and we mix it with oxygen. And heat it enough, it will combust. This is a combustion reaction. So if you've got like natural gas or something, let's get with a little bit of methane in it, and we burn it. This is essentially the reaction that you get at that happens there. But we can go in and look at this. We can go in this and look at this in terms of redox chemistry. So what we would do is we would go in and we would assign the oxidation state to all of the individual atoms here, and that will tell us what's being oxidized and what's being reduced. So for example, if we look on this side of the reaction, so we've got hydrogen here bonded to carbon, and we want to figure out what all the oxidation states are. So hydrogen we know has a +1 charge on it. So I'm going to do this kind of in my head just to keep things from getting super messy. I don't know if that helps. I'll put this in red. Maybe that'll help. So this has a +1 on it. And so the total charge that we get from the hydrogen, because there's 4 of them, is +4. So that means that our charge on carbon, let me use green for that just to be consistent. Try and use green for oxidations. But yeah, so if I have +4, that means that the carbon must be -4, because the net charge on this thing, right? We don't typically write it out, but the net charge here is 0. So I know that these things have to sum up to be 0. So +1 times 4 gives me +4. And so that tells me that this must be -4. All right, so but then I can come and look at the other side here. And I can say, well, what's the charge on carbon on the other side? So I come in, I have carbon dioxide. I know it says O2, but just in general, there's very few things that are actually peroxides. Like aside from H2O2, I don't think you have to worry about it. So generally, oxygen's going to be -2. But okay, if the oxygen is -2, so if this oxygen is -2, and I have 2 of them, that means it's actually, I've got a total of -4 up here for the oxygens. So I need to balance that to where it'll end up being 0. And so I put a +4 right here. And so now we see that the carbon has changed oxidation states as we go from one side of the reaction to the other. And since it's becoming more positive, that means that it's losing electrons. And a loss of electrons is an oxidation. And this you can kind of see where the word oxidation comes from, right? It is truly being oxidized in the sense that there's oxygen that's being added to it. That's I'm assuming historically the origin comes from looking at adding oxygen to something usually increases the oxidation number on it. But yeah, so in this combustion reaction that is reasonably familiar to most people, what you're really doing is you're taking carbon and you're oxidizing it to carbon dioxide. So methane, once you react it with oxygen, it gets oxidized. Yeah, you're literally adding oxygen to it. So if we know that something's being oxidized, then we know that also in that reaction something must be getting reduced. So what is our charge on oxygen over here? It's just going to be 0 because it's diatomic oxygen, and we talked about that for assigning oxidation states. When we come over here, what is the charge on oxygen going to be? It's going to be -2 because oxygen is always -2 unless it's a peroxide. And this makes sense with what we know about hydrogen, which is that it's +1, because +1 times 2 gives me +2, -2 gives me 0. But yeah, so what's happening here then as we go from this side to this side, as we look at the oxygen, we see that it's picking up negative charge. So I'm going from 0 to -2, so going more negative. That means I'm picking up electrons. So as things become more negative, that means I'm gaining electrons. And so what is this? This is a reduction, which is what we expect. So if you end up in a situation where you think you're getting like 2 oxidations simultaneously, either that question is written wrong or you messed up. But yep, so this is how we look at oxidation and reduction reactions. Not all reactions are oxidation reduction reactions. I mean, that's what we're going to be talking about in this chapter. So you can generally assume that when you're given something, it's oxidation reduction. But there are plenty of reactions that do not involve electron transfer in this kind of way. But yeah, so this is an oxidation reduction reaction with things that get a little bit more complicated than the top one. So, this is maybe like a simpler case where you're looking at just like single atoms on either side. Here, you're looking at the oxidation of carbon, but it's bonded to different stuff. Like here, it's got some hydrogens, and over here, it's got some oxygens. Okay, so yeah, so let's take a look then at how are we doing on time. We get 12, 13 minutes. Here we go. Questions. No, that's a good question. So the question is is there a term for the thing that gets oxidized or reduced, or for something that doesn't change oxidation state? So for example, hydrogen here is +1, and then you come over here and it's still just +1. Do we have a special term for that? Kind of like with ionic reactions where we have what are called spectator ions? No, there's no name for it. Just not that I'm aware of, at least. Yeah, there's no special name for this, but we just need to find somewhere in the whatever the chemical reaction, like regardless of what's going on with all the other atoms that aren't changing oxidation state. We just need to find the atoms that are changing. So I think, I'm trying to think if this is true or not, but I think typically what you'll see is it's just two atoms, or two atoms that'll change oxidation state. So here it's the carbon is getting oxidized, and the oxygen is getting reduced. Yeah, and nothing's happening with the hydrogen. But you can have molecules that are more complicated than this, and still it'll just be two atoms that change oxidation states typically. Yeah. Oh yeah, the oxygen, that's a very good point. Yeah, so because the oxygen's combining with carbon over here, you have sort of reduction happening in two different places. That's a good catch. But still, even when I'm saying like it only involves two atoms, it's still just carbon and oxygen, even if it's happening twice over here. So you're oxidizing both the carbon. You're not really oxidizing hydrogen, just the bonds are kind of swapping out there. But the oxidation state on oxygen is changing. Yeah. And then I guess if you want to just for completion's sake, like what's the oxidizing reagent? What's the, let's say the oxidizing agent is going to be oxygen because it's what's being reduced, and the reducing agent is going to be CH4. So when you talk about what's like the agent or whatever, you're talking about the whole compound. You don't say like the reducing agent is the carbon, it's the CH4. Let's see. All right, so if you understand how to deal with oxidation states and assign them, aside from some introduction of some vocabulary here, this stuff's not too complicated. The balancing of redox equations, which we're about to dip our toe into, I don't know if we'll actually get through the full balancing, is a little bit more of a pain in the ass. It's not like, what do I want to say about it? It's just a pain in the ass. There's no other way to describe it. It's not like incredibly difficult. It takes a good amount of work to balance one. So like even if you know what you're doing, it just takes a while to do them. But once you sort of have it down on how to do them, it's straightforward. So step one is learn how to do oxidation numbers. That's your very first step. You need to be able to assign oxidation numbers. Step two is, be able to use some of this language, oxidizing agent, reducing agent. But then step two is learn how to do balancing of redox reactions. Let's start with let's look at a straightforward one. So when you're not in, these are not that bad. Well, look, we'll just make them progressively worse. We'll start with a simple one though. I'm going to leave off the states just because it makes things messier. So ultimately what we're working towards here, I know this is kind of dry, but ultimately what we're working towards here is you can take these types of reactions where you have electron transfer, these oxidation reduction reactions, and make a battery. This is how batteries are made. Like lithium ion batteries and stuff all work off of this kind of idea. And so there's a way to, derive energy off of these reactions as they progress, or do work, I guess, with the energy from these reactions. So if you're an engineering student, we have John Goodenough in the chemical engineering department who got or at least shared the Nobel Prize. I think he shared a Nobel Prize with I don't remember who, because I'm not in that field, but for inventing our contributions to the lithium-ion battery, which is the basis for like your cell phone and the Tesla cars and all of the different laptop batteries and all these different types of batteries. And it works off the same fundamental principles. Okay, so we've got this reaction here, and let's say we want to balance it. So the starting point is to assign all of the different oxidation states. So again, you should be you try to get to the point where you can kind of do it in your head. So oxygen is -2, and we've got 2 of them. So this whole side over here is going to be -4, which means that manganese is +4. Aluminum is by itself. And you see that the way I've written it, there's just nothing written on it. And same is true for manganese. So both of these have an oxidation state of 0, which I'm going to write in. And then lastly, over here we have alumina. And so we know this has a -2. -2 times -2 times 3 is -6. And so we need this whole thing to add up to 0. We have 2 aluminum here, so we know that this needs to be 3. So the math I'm doing is 3 times 2 is +6, and then 3 times -2 is -6. And so that gives me what I want, which is a 0 for this. Yeah, again, if that's not making sense to you, that's okay. It just takes practice. I just can't spend too much time on it in class because we have a bunch of stuff to get through. But if you hang out at office hours and you want to work on that, that's a good time to do it. All right, so we can go through this and identify what's being oxidized and reduced. What's a good way to, let's see. Let's do it this way. Let's break it up into, let's break it up into half reactions. So what was I using for reduction? Oxidation, I'm using green. Okay, so let's identify what's being oxidized here. So oxidized means that the oxidation number is increasing. And so if we look at aluminum, it goes from 0 to +3. So that's our oxidation reaction. And if we look at the other one, which is manganese, that goes from +4 to 0. What's happening with the oxygen? Nothing. Just -2, -2. We're not super worried about that. Okay, so the first step for a lot of these balancing, there's a lot of different ways to balance these things, but usually people use what's called the half reaction method. The first step is just to break it up into the 2 half reactions. So I'm going to break it up into the oxidation on top. I'm going to break it up into kind of 2 separate reactions. And the purpose of this, it doesn't have any real physical meaning. It's just it's just a way to look at it that makes it easier to balance. So I'm breaking it up into its 2 separate reactions. So I take the oxidation reaction, which is that the aluminum goes to, yeah, aluminum goes to aluminum oxide. And then I take the reduction reaction, which is that manganese goes to manganese 0. So we're probably going to have to stop pretty soon. So this is step 1 for balancing them, is break everything into half reactions. Step 2 is balance like, I want to say metal, but balance the, yeah, because it doesn't always have to be a metal. Balance the, yeah, balance, oh, I know. So balance all elements that are not hydrogen or oxygen. So in step 2 of this, we just want to balance out things that are not oxygen or hydrogen. So yeah, these oxygens we don't mess with. But you see here at the bottom, well, let's get the bottom first. We got manganese on one side, manganese on the other. We have 1 of each, so we're fine. We don't have to balance that. But for alumina, we do actually have to balance this because we have 2 here, but we only have 1 over there. So we balance that with a coefficient of 2 there. Okay, yes, all right, so now class is ended. So we'll pick up, so we're kind of, I mean, follow along with the LEs, because I think the LEs they made for this, for Unit 4, are particularly good and have really good lectures and stuff in them. So, but yeah, we're going to work on balancing redox reactions. We'll finish this out, and we'll probably work through one more on Wednesday. Let's see what else we got going on. Yeah, we'll do that. We'll work through that, and then hopefully we can get started on electrochemical cells on Wednesday and start talking about that. But yeah, try to keep plugging away at this. I honestly, I feel like for most students, what gets them is just assigning the oxidation numbers. A lot of students just kind of stump there. But yeah, then next step is kind of identifying what's oxidize and reduce and trying to break this up into half reactions. This, I'll say that as much of a pain in the ass as it is to balance redox reactions, it is like very like formulaic. It's like do this, then do this, then do this, then do this, and you always end up with a balanced equation at the end. It's just, there's a bunch of steps. So yeah, so in the 3rd step, we'll look at balancing oxygen and how to balance hydrogen. And then finally, we'll balance out the charge for the electrons. And then we can add our half reactions back together. So it's like this kind of, 10-minute long process to get one balance. And it varies if you're doing an add. There's a few different like caveats and stuff with that. So yeah, so we'll finish out balancing redox reactions on Wednesday. And then we'll get going in electrochemical cells, which are a little bit more interesting. That's when we start talking about. Yeah, so so you might have been taught a different way in high school to balance redox reactions. I don't know. You can use whatever way you want as long as you get the right answer. But you don't mess with this. I mean, this one you might be able to do by inspection, but generally you don't want to mess with just kind of like trying to fidget with this and like, put a 2 here and then balance out the oxygen by putting a 3 there. That's not how you want to deal with these. So this is not a standard balancing situation. It's a different approach. So yeah, so balancing redox reactions is a separate thing from the way that we normally balance reactions. It's not to say that it doesn't work to balance it the normal way, but most of the time you can't get there and I'll show you why that is when we pick up on Wednesday. So for example, we're going to use, yeah, I don't want to make it more confusing, but work on assigning oxidation states and being able to break this up into two half reactions. That would be a good place to be for Wednesday. If you can get ahead and look in the LEs and follow what they're doing in there and actually go through a couple of redox reactions, that's even better, because then you'll learn more the more prepared you are. But yeah, we'll work through another one of those, and then it'll just kind of be on you to kind of practice a whole bunch of those, and then we'll move on to electrochemistry and looking at electrochemical cells. We have another really famous electrochemical guy in the department too, Dr. Bard. He's in the actual chemistry department. No Nobel Prize, but still super smart guy. So anyway, all right, cool. I'll see you guys in like 5 minutes or 10 minutes if you have questions in office hours. This stuff's not super challenging, but it does take some work, so don't slack off on it. You guys have questions? We just had an exam, so it's not a lot of material to go over, but.
Can we talk about some exam questions if no one has any oxidation redox questions?
Say that one more time, Taylor.
If no one has any redox questions, can we go over the exam questions?
Yeah, for sure. Let me get the exam up. Does anybody have any questions about oxidation stuff? No. Yeah, I figured you guys want to talk about the exam. Okay. Two, three, 4, 5, 6, 7, 8, 9, 10, 12. With 12 is the molar solubility one. Highest to lowest solubility. I think I should say probably molar solubility. Yeah, so the deal with 12, when you're talking about solubility, is it's not. Where did my tab go? There we go. So we have all these different. I think this was in the review session that the TAs did, but you have all these different compounds with different KSPs. And so the instinct, I think, is to just look at the KSP and assign the solubility based on that. Which is not a bad instinct, but you have to remember that the KSP is dependent on, is sort of related to the, like, I don't want to say like stoichiometry of the salt that's going into, that's dissolving. I'll show you in a second what I mean by that. Like I guess what I'm saying is the KSP is not, it is a measure of the solubility, but it's really a measure of like the equilibrium between the solid and the aqueous components. And so it's a little bit trickier than just looking at the KSPs and assigning it from that. That's not right. Point 0.2 times. Yeah, so if we write out the KSP expressions for these, so we're talking about solubility, we're saying, you know, like literally if I put this in, like how much will go in, which one's the least soluble. And so the KSP is related to that, but it's not identical. So you want to write out, you can write out your KSP expression for these. And for the first two, it doesn't really matter. You can compare those by KSPs. By looking at. But it's these ones down here that get a little wonky. And so when we're looking at the solubility, for example, of silver iodide, the amount of silver iodide, let's say you're starting out with 0 of each of these, the amount of silver iodide that goes in is, you know, like let's say we didn't know, so we'd call it plus S. It's going to be plus S for both of these. And so you end up with an expression for whatever the solubility, I guess, like whatever S is equal to here, because it's 1 mole, is going to be equal to the solubility of whatever the silver iodide is. That's sort of the way to think about it. Like if like 1 milligram, so like let's say you put this, I'm going to talk in milligrams instead of molar quantities. Like let's say you put in this chunk of silver iodide, and no, I should talk in terms of moles. Let's take it back. Let's say you put in a chunk of silver iodide, and 1 millimole or 1 mole or whatever of silver plus goes into solution. You could say, well, how much silver iodide went in a solution? And it would be the same amount because they have the same stoichiometric coefficients here. So for every mole of silver that dissolves that you see in solution, that means a mole of silver iodide must have dissolved in solution. And so the solubility of silver iodide is just going to be equal to S. So we could say, if we try and take this equation up here and solve for it, we would say that the KSP is equal to S times S. And so what we want to find there is, what we want to find is S. That's ultimately what the solubility is of the, whatever the compound is over here. This one, it just works out nice and cleanly because the stoichiometry, because these are just, they have a subscript of 1 on them. But so S would end up equaling the square root of the KSP, which would equal the square root of 8.8 times 10 to the minus 17. And so that's basically your workflow for finding the solubility of these things, though. So like if you want to find the solubility of barium carbonate, you do the same thing. You'd say that one works out to be like similar in terms of this workflow. So this would be silver iodide. So we'd end up writing out the same expression. So solubility for barium carbonate would just be S is equal to the square root of 2.8 times 10 to the minus 9th. So you can see that like it doesn't really matter for these two because they have the same subscripts on them and they break up in solution in the same way. Like if I wrote out the reaction for barium carbonate, it just looks like this. So what we end up losing is going to be, you know, plus S and plus S. So it doesn't really matter. You know, like if I take the square root of both of these numbers, relatively speaking, it's not going to change which one has more solubility, just comparing their KSPs. But when we get down here to look at like cadmium arsenate or whatever, now when I write out my expression for it, I see that I pick up this 3 as a coefficient on the cadmium and a 2 on the arsenate. And so now, and so that's going to change not only the how we express their relationship through the stoichiometry, it's also going to change their expression in KSP. But you see now that like S is which we're ultimately solving for is S. But if we see like, you know, 1 millimolar, let's say 3 millimoles of calcium in solution, that means that, I'm sorry, not calcium, that should be cadmium. If we see 3 millimoles of cadmium in solution, then we know that 1 millimole of cadmium arsenate dissolved. And so that's sort of the relationship there. But yeah, we end up with an expression now of KSP is equal to 3S cubed times 2S squared. And so now we have to solve, yeah, now we just have to solve this. So now we end up with 3 cubed is 3 times 3 is 9, with 27 S cubed times 4S squared. 27 times 4 is 100 plus 2 times 4, 108. Do my calculator. Yeah, 108. So yeah, so S ends up equaling the 5th root of KSP divided by 108. And then yeah, for the last one, it's the same kind of workflow. It's cadmium hydroxide. So we end up with KSP is equal to S times 2S squared. So that ends up being 4S cubed. So S equals the cube root of KSP over 4. And so we can plug in some values for that. What do I have? KS 2.2 times 10 to the minus 33. But so you can see how it affects the how you express the solubility of the compound, because now we're having to take the fifth root of this number as opposed to the square root, and so you're going to end up with a smaller number. So ostensibly, when you just look at the KSP, you're like 10 to the minus 33 is very small, but if you don't account for this, like these coefficients, and these roots and stuff that you end up taking, then you can misestimate which one has the highest solubility. 2.5 times 10 to the minus 14. Let's see, I don't know, we need to go through every single one of these, but let's go through this fifth root one. The fifth root of 2.2 Yes, our solubility there equals 1.15 times 10 to the minus 7th. I did put that in my calculator right. 1.8 times 10 to the minus 5th. And then, yeah, whatever the square root of 2.8 times 10 to the minus 9th is. So yeah, so when you come out and you actually calculate S for these, we see that for silver iodide, we have 9.3 times 10 to the minus 9th molar. For barium carbonate, we have 5.3 times 10 to the minus 5th. For this cadmium arsenate, when we have 1 point, let's just call it 1 times 10 to the minus 7. And then for this one, we have 1.8 times 10 to the minus 5th molar. Right, yeah. So yeah, so, like at first glance, it feels like it's got to be this one because 10 to the minus 33rd is such a small number. But when you actually go through and calculate the solubility of it, like the molar solubility of it from the KSP, we see that it's 10 to the minus 7th. And so even though this number is smaller, the KSP is smaller than it is for silver iodide, when you actually go through and compute the molar solubility, we see that the silver iodide actually has a lower, is less soluble in water than cadmium arsenate. So the main thing is just that the KSP is an indication of usually of the solubility, but the the value for KSP can get sort of bloated if you have like some subscripts on here that result in, like we come down here, that result in having coefficients on the products because you end up with these cubes and these squares. So, when you cube and square the concentrations here, it makes the KSP look really big, which it is. It's not like that's not an illusion, but it gives the false appearance that the solubility is smaller than it actually is. So that's how that question works.
I don't want this to come across the wrong way. I mostly just want to point out why I think I missed this.
Yeah.
Because on the question, it's just asking us to order in terms of solubility and not specifically molar solubility. And the definition of the KSP from the GChem website and some that I've pulled up online basically says that the higher the KSP value is, the higher the compound solubility is. And it kind of says that straight up. And so I wasn't able to attend that review session because I had to work. I glanced at their slides, but I wasn't able to see that these are two different things. So my question essentially is, if it doesn't say specifically molar solubility, how as a student was I really supposed to know that I had to solve for that rather than just take the KSP based on that definition in the GChem book?
I'd have to look at what the GChem website is. It shouldn't say. I understand your point. I think molar solubility would have been a better wording of the question. But usually when you're asking about solubility, that's how you define it, is in terms of like how much of it goes in a solution. The only other thing it could be besides the molar solubility would be like the mass solubility, like milligrams per liter or something. That's what I was thinking about when I said they should specify molar. So it's kind of implied, but the KSP, it shouldn't say that the KSP indicates. I have to look at how it words. It shouldn't say that the KSP indicates. I'm trying to be careful with the language here. I understand that it's confusing. It's not that the KSP indicates the solubility. Sorry. So the KSP does tell you the solubility. And the lower the KSP, generally the lower the solubility. Let's see. Yeah, let me look at the GChem website. But yeah, I think I understand why it's confusing. It's not that the KSP allows you to calculate the solubility of a compound. It doesn't necessarily tell you the solubility of the compound directly. The proper wording for it is that the KSP is the equilibrium constant for the solid and the dissolved ion. And that's sort of what we see kind of fall out of this question. We must have had, I'm pretty sure we have homework problem like this in the modules though, right? In one of the learning exercises. That's how I expect you to kind of know how to solve the problem.
Yeah, I looked through them after the exam. I had worked each of the homeworks 3 times in preparation. And I looked through and I couldn't find one that was very similar to this. I'm looking through the GChem website now to see if I can find
number 12.
Homework 6.
Yes.
Let's see.
That's definitely possible. Because I didn't work those because I didn't think about them since they were kind of under the previous unit.
Oh, because it just because of the way they're organized in the module thing.
Homework 6, question 12, if I'm on the correct one, is just talking about a net ionic equation.
It's number 19.
Number 19. Okay.
Yeah.
Yeah, that's definitely a very similar question. I guess I
20,
just
yeah.
didn't think to go back to that one.
I mean, it's not meant to be a trick question, but it is the instinct, I think, is to look at the KSPs and just say, yeah, this one is lower. So yeah, I guess question 20 even has cadmium arsenate in there. I don't know. It wasn't like, I mean, I guess it, like, to your point, it wasn't like super stressed in class as far as how to do this. I think we went over a little bit in office hours, like with the how the molar solubility, or like what S actually means, but I don't know that I explicitly worked one of these problems out.
Yeah, I mean, I wouldn't expect you to work out a problem for everything that comes on the exam. I'm just basically, I went about that question based on the definitions and the notes that I had read through, which I'm still looking for. I found definitions that fit what I'm saying online, but those are from websites and not from y'all's website. So I'm still looking
Yeah,
through y'all's.
you got to be careful with that. If you
Mm-hmm.
can, if you can find something on the GChem website that says like the higher the lower the KSP, the lower the solubility or something, then um, just send it to me and I'll take a look at it and think about it. And let Dr. McCord runs that page. I'll let him know that that needs to be updated. And you know, it is. It's like a half truth to say that, even that the lower the
Mm-hmm.
KSP, the less soluble a compound is. Um, yeah, it just doesn't directly compare, I guess, is the problem. Uh,
Yeah.
like I don't know how to say, I'm like trying to think of a way to like word it to where it makes sense, and it's just like it is true if something has a very low KSP, generally it's going to be very insoluble. But yeah, it's just that the numbers that you compare, if you compare two KSPs, it doesn't compare exactly. Like the relative numbers don't work out perfectly. So
Yeah, I mean, it makes perfect sense why my answer's wrong. I'm just trying to figure out kind of why I missed it.
yeah, I mean, um, yeah, I mean, we could maybe. I mean, part of the problem, I guess, we left off solubility from our last exam, and so it just kind of like got crammed onto the front of this exam and doesn't match the kinetic stuff super well. Like it's just sort of an extra tidbit. Uh, as far as everything else, like the kinetics, it forms like a pretty cohesive picture. It's like all kind of part of the same pie, whereas this is like a separate thing. So I feel like that probably plays a role as well. So, but yeah, if we'd have put it on the acid base stuff, I just felt like that was already, people struggle with that, so it wasn't a good place to put it either. I don't know, but yeah, let me know if you find something on the GChem website that like gives that false impression, and I'll think about giving some credit back or something. I know it sucks to I know, especially on a multiple choice exam, it sucks to miss questions. And then it's like, yeah, once you know the workflow, it's like, okay, that's not that bad. But honestly, I guess like having things be open book, it's like you just being able to like use Google and like know the search terms can be pretty helpful. All right, let's take a look at some of these other ones. I hate when they don't put problem numbers on here. All right, so we got, which one is 18, Taylor? Can you just tell me like what the sentence is so I can look at it that way? I don't have to count.
A saturated solution of copper phosphate and sodium phosphate has a saturated solution of copper phosphate has sodium phosphate added. What will happen? Select all that apply.
Okay, let's take a look at this one. Yeah, I don't know how you all did specifically on the exam, but the grades seem better for this one. But yeah, it seems like the solubility stuff is maybe a problem. Maybe I should have spent more time on that in class. All right, we've got copper phosphate and sodium phosphate. Copper 1 phosphate. Ugh, come on, brain. Okay. You're not going to form anything. Copper phosphate is pretty insoluble in general. Copper phosphate. I guess it's saturated. Okay, so you've got two. Okay, yeah, all right. Sorry, I'm trying to imagine the setup. So I think, so they're saying it's saturated, so that means you've got some copper and phosphate in one flask. And we've got sodium and phosphate in the other flask. And we're going to dump those together. And so, yeah. Copper phosphate will precipitate. Is that true? I guess they're both saturated. I'm trying to think of what the concentration, because you have to account for the fact that the concentration of copper is going to go down. But your phosphate's going to go up. Oh, no, okay, I'm sorry. I'm misunderstanding the question. Okay. I thought you had two solutions. That makes the problem not fair. Yeah, so I have copper phosphate. This is saturated. Okay. And now I'm adding sodium phosphate in. And we're saying what's going to happen. Okay, that question makes a lot more sense. Yeah, so I've got solid sodium phosphate. I'm adding it into saturated copper phosphate or whatever. Yeah, so for sure, copper phosphate is going to precipitate. And the reason for that is if you, let's say what's the most straight, like, let's say you write out the equilibrium expression for it. Let's get rid of this, it doesn't matter. +1, and then we have phosphate over here, which has a -3 charge on it. So you've got this solution. And so this is a Le Chatelier's principle type thing. If I'm adding in, this is the common ion effect. So I'm adding in phosphate, which is common. That's the common ion in the product. So that's going to shift the reaction back towards this direction. And so if this thing is saturated, that means that you're going to form some additional copper phosphate at the bottom. Does that part make sense?
Isn't copper phosphate already insoluble? Because phosphate is insoluble, so isn't already a precipitate, I think.
Yeah, I can see why that's confusing. That was honestly my first thought, was that it was going to be like one of those solubility type reaction problems. So I think what the lesson from the solubility thing is that even things that are insoluble, like copper phosphate, if you were to talk about it, like you would talk about it as an insoluble salt, but we kind of learned that even things that are insoluble can be slightly soluble. Wait, sorry, say what you were saying again, Taylor. Maybe I misunderstood.
No, what you're saying, I just thought that copper is insoluble with phosphate, so copper phosphate is already insoluble. So
Yeah,
I thought it would already have precipitated out, but you're right.
Yeah.
They don't. Nothing is completely insoluble. So.
Yeah, that's the trick. And you know, like that's the first place my mind went to. I was like, oh, copper phosphate is completely insoluble. but then they tell you it's saturated. So like, you know, it's saturated. That might be like a teeny tiny amount of that in there. But that does imply that you have some copper and phosphate dissolved. And so yeah, so that's the trick. Yeah, so this will cause some more precipitate to do it, which is another way of saying that the solubility of copper phosphate will decrease because again, the common ion effect, it's going to skew everything back to the product. What's this last answer here? I can't read that one for some reason on here. Dissolution reaction equilibrium. I think they're just saying, probably what I'm saying here is that the equilibrium shifts towards the reactant side. So. Yeah, Tugger, you can hang out for a little while afterwards. I don't know how long, a couple of minutes yet, for sure. Just hang around and we'll chat. All right, so that's 18. So then this is 19. So 20 is mixing potassium hydroxide and calcium nitrate. So we've got this. Ugh, I hate these questions. I did not write this question. They're not bad questions. I just, the which of the following statements is correct are always just a pain. They're not the worst, I guess. I mean, like it's a way to make the multiple choice questions a little bit more difficult. I think for me, I end up too like hyper analytical around them. All right, let's see. So which of the following is a solution is unsaturated? Let me see if I can expand this window out. Yeah, we go. Nope. Calcium hydroxide participates until the solution is saturated. Solution is unsaturated and no precipitate forms. Presence of okay, all right. Sorry, it's hard for me to read the answers on the way that it presents in my browser. Let's see, I think all you're doing here is, yeah, you're saying, you're trying to figure out what happens here. So what you do is you look at the KSP and you say, so in this case, all right, so our KSP here is 6.5 times 10 to the minus 6. And all that means is, that means that the concentration of calcium times the square of the concentration of the hydroxide, if it's less than the KSP, then you're fine. Nothing's going to precipitate out. But if it's greater than the KSP, then you're going to form a precipitate. So all we have to do is take the calcium concentration, which is 0.001, and multiply that times 0.015 squared. And what we get is 2.2 times 10 to the, or 2.3 or something around that. Doesn't really matter. 2.25 times 10 to the minus 7. I guess it is units molar cubed, but this is the number that you get based on these concentrations you're given. But since that's less than the KSP, then you're fine. It just, nothing precipitates out. Everything stays in solution. The KSP sets sort of the solubility limit. So it's like as long as the concentrations that are here, like in this expression, are less than that, then you're fine. It's not until you get above that, above this number, that you actually start to see some precipitate fall out. So like, for example, if we increase the amount of calcium to where this number now is going to be like, 1 times 10 to the minus 5 or something, then we're going to start to form precipitate. But up until that point, it's soluble. Does that make sense? It's sort of, if you want to get really like, you could call it, it's sort of like you could call this Q. You could say like Q is equal to.
I understand.
Okay. I try to avoid the Q thing because but yeah, that's basically how the solubility works. And then we've got, I got 1. I'll go over 1 as well. Sorry, I missed that. 21. Oh, it's just a multiple choice question. Which of the following statements is correct? Not select all that are correct. So 21 is the last one. We've got, oh good, it's a kinetics question. Let's see, we've got ammonium and nitrous acid forming nitrogen gas and water. What is the average? They're asking for you to calculate the, I guess it's sort of like the instantaneous rate. But so we've got initial concentration of HNO2. One molar. And then after some amount of time, 28 seconds, I'll just call that T, falls to 0.82 molar. And T is equal to 28.8 seconds. Let's see. What is the average rate of the reaction? Looking at change in time. Yeah. This one is all they're asking for. So they're asking the average rate. You can think about it as I'm trying to think of like if you're in like a car or something. Like if you're like, I'm going 100, if you're going 100 miles per hour, let me think about that. Is that the right way to think about it? Because time, concentration is more like distance. Yeah, it'd be like if I started, the way that what they're asking is like, it's like if I'm, let's say I travel between, point A, or let's say I travel 5 miles, and it takes me, 1 hour to get between point A and point B, which are 5 miles apart. What's my average rate? Rate, let's see, rate is the right way to think about that, right? Yeah, miles per hour. Velocity. Yeah, all they're asking is what, that's all they're asking for here. So, what would you say? You'd say, okay, well, it's on average, you were going 5 miles per hour as you went across. And that's exactly what they're asking here. Only now, instead of traveling between a distance between point A, I guess the right way to say it would be like to really set it up similar to the problem. No, I think that's kind of how you have to do it. Like, yeah, there's 5 miles between these. But here, yeah, it's like saying, okay, if I start out here at 1 molar and I travel to 0.82 molar, the amount of time it takes me to get there is essentially the rate of the reaction. So you're calculating, what you're doing is you're just calculating this. So remember, we define the rate of the reaction. Is this, so you're just calculating that out. And this is what, if you were to expand that expression, it's like, yeah, if you expand that expression, it looks maybe something like this. So if you take it and you say, okay, well, we've got 1.00 molar minus 0.82 molar, and we divide that by 28.8 seconds.
So it's initial minus final.
Yeah, I think that's the tricky thing, is initial minus final, because yeah, because like
Yeah.
I guess that's where the kind of the yeah, okay, I see your questions. Yeah, I guess normally when you think about like traveling, if we're thinking about traveling in a car, you take your final point. Let's see. Yeah, and you would subtract that from. Oh, I see what you're, because it's delta. Let me think. Why is that true? Yeah, I mean, it's weird because, yeah, usually I do think of terms of final minus initial when I think of delta, but like the change in concentration has to be, it's not going to change in the opposite direction. And you're not going to end up with, let's see, minus 1.8 or something.
Well, it's supposed to be decreasing, right?
Yeah. No, I mean, like, it makes sense. It makes sense intuitively to me that it just, that's how you would set it up. But usually when we say delta, it's final minus initial. But the change, if we're just thinking, just forget about that. The change in concentration, which is we start out with 1 molar and we end up with 0.82 molar. So what's the difference between those two? It's going to be whatever 1 minus 0.82 is.
When we
I see. But yeah, I guess if you want to say it's negative, sure. Yeah. Okay. Fair.
Okay.
Yeah.
Okay, so the correct answer would be positive 0.063.
The negative should work as well, right?
Yeah, you get the same answer regardless.
Okay. But then
Yeah.
the negative one is counted wrong.
Well, let's see. There is a negative one and it's counted wrong.
And we know that's a reactant, so it should
It should decrease. Yeah, I agree. The aperture of the reaction.
They went over like a question similar to this, or on the TA's reviews, but they specifically said like reactants, their rates are negative, and they said for products their rates are always positive.
Yeah, no, I agree with that. I really, I mean, honestly, for me, either one is fine. Like in my mind, it's like, yeah, I guess maybe if you're like working kinetics or something, it matters, but because it's not like because it's not like, yeah, it's almost like it's like if you were thinking in terms of like a car or something, it's like it's almost like you're, yeah, I don't know. Let me reach out to Ryan about that one. I'm compelled to give, or I'm sorry, not Ryan, Samoilenko about that. I'm compelled to give credit back for that one. Unless there's something I'm missing that makes sense for it to be negative. My instinct was to calculate it out by taking the starting concentration. Well, okay, let's see. So it's being consumed. Yeah, I don't know. It probably should be negative. Let me ask. Let me circle back. But yeah, let me say maybe we can give credit back for that problem. Like I think not only, I could be wrong because I don't think about reaction rates that much, but I think not only do I feel like, either positive or negative, it's not that big of a deal which one it is, but I think negative is the correct answer. So at the very least, we could make both. I feel like we could just make both acceptable answers. 0.028. That I bet you shouldn't come out with that, but yeah. Yeah, I guess for me, like when I think about signs, I think of them as being somewhat arbitrary. But I mean, I guess you also have to follow whatever the convention is for the science. But yeah, whatever. You guys know what you're doing there. I don't see why you should miss that question. So I'll just go in and change it now. Fuck it. Okay. All right, I just waved a magic wand, and it is. You should get credit back if it was negative. Yep. All right, cool. All right, I am going to end office hours, except for Tucker. Why don't you hang back so we can chat, and then I'll see you guys on Wednesday, and we'll finish out this Redox stuff and get through this pandemic.
Thanks for your help.
Have a good day.
Yeah. Give me 1 second here, Tucker. Let me boot some people out.
Yeah, no rush at all.
Okay. All right, now it's just you, man.
Okay, perfect. So for this question specifically, and then I might have some other things I'll ask you about, but I'll make it quick for you. I'm looking through it, and it doesn't really say anything for or against what my thought process was. There's a page that is titled KSP to solubility, and it's basically talking about converting between the two, but it never really says that the KSP isn't a valid thing for determining solubility. And I remember that there was a point while I was reading this that I looked up what does a higher KSP value mean, and when I had Googled it, it said what I had said before. So basically that's, for me, and when we're in class and in person, I'm one of those annoying students that comes and asks you a bunch of questions So that's probably one that I would have asked. But yeah, there's nothing on this page that really makes me think that KSP wouldn't work for that. And when I Googled it, it said pretty clear and straight up. So I moved on that a higher KSP value relates to something being more soluble. But just in terms of that question, if you can't give me anything back for that, that's fine.
I mean, how are you doing in the class? Is it a high stakes situation?
It's a very high stakes exam. To be completely honest with you, I've never made a B in chemistry in my life, but I find myself in a big hole in this class. And I don't think that has anything to do with you or quite frankly me. I've really struggled taking these things on my laptop. Number one on this exam was a really bad mistake. I had to come right after work, so I just made a dumb error on that. Number 8, I talked with Ryan about it, and I did my work perfectly, and then I didn't raise 2 to the second power and then divide by 4, just divided by 2. So basically, like a calculator error, and then I basically got it to be x was equal to 9 times 10 to the negative 5th, and the answer was 7 times 10 to the negative 5th. So basically, I chose the answer that appeared somewhere in my calculations, thinking I was right. I didn't really, I had a 50-50 guess, and I guessed wrong, but a calculator error made me miss it. But basically, the story of my semester has been, I feel like I know this stuff well. And then
the test comes,
just taking it on my laptop, I've struggled. So I don't know. I've thought about what I could request for that. I do feel like I've had this happen. What's that?
Like accommodations?
Yeah, I mean, I don't want to ask for anything that's not fair to other students. But one thing that I think might be fair would be maybe if 100% of my grade could be the final. I don't know if that's possible.
Yeah, I mean, I've had that type of thing. I have to. What? Let me think about it. I'm sorry. I'm pulling up your grade right now. Exam 3 doesn't. Why didn't exam 3 show? Oh, there's exam 3, 89. Oh, 89. I'm going in 4, but that's still a good grade, right?
It's an 85, which is, like at the end of the day, if I get a B or a B plus in your class, that's fine. It's just going to be painful because I think that's 100% that it's been an online exam every time. But
how was it? Well, I guess exam 2.
Yeah, exam 2 was tougher. But basically, if I did well on this one, I'd be in position to make an A. And
I see.
A calculator error, and then a dumb mistake on number 1, and then obviously misreading number 12 took me from 100 or a 95 to an 85.
Right. I see. So yeah, you're like in that solid. Let's see.
I could show you my work for number 8, but
no. I trust you that you're doing well. I have to balance some idea of fairness with the rest of the class. I agree with you. It sucks that you're on I don't know. I'm anti-exams and grades in general. So it's, I think it's all, I don't know how accurately any of these things assess what students know, but it's just how people do it in college. So, but yeah, whatever I do for you, I may have a little bit of leeway, but 86. Yeah, I mean, I'll quietly on the side, I'll make a deal with you. If you get an A on the final, sure, I'll give you an A in the class. But it looks like I don't do the grading scale up. It looks like you're solidly in the B range, right?
Yeah, I mean, I don't think, has exam 1 been corrected for its grade?
Corrected in the wrong. I can pull your grade up.
Because I made an 88 on that one.
Oh, okay, and it's appearing lower than it is.
Yeah, I think so. Yeah. It had subtracted 2 of the questions from me.
I have it in a Google Drive. No, it hasn't been corrected, but yeah, I have it. It's just a mess. I have it in an Excel spreadsheet where I finally have it outputting, I think, the correct grades. But then I have to go back. I don't want to lower anybody's grades. So, but yeah, you're fine. I mean, so I guess we still have exam 4. So let's see. So if you get an 88 on the first exam and an 85 or an 83, and you do well on exam 4.
I think I can scrap together an A-. I think I could, but in terms of an A, I don't think I can. I've calculated it a little bit myself, but
yeah. Let's see how you do on exam. Let's see how you do on exam 4, and then see how you do on exam 4, and then we can. Let me think about the final. So you get 1 drop exam, 88 and 85. Yeah, you'd be pretty close. Let's see if you do well in exam 4 and do really well in the final or something. I can think about weighting those a little bit more. Like if you're really close to an A or something.
Yeah, and I'm confident that I'll do that because this exam, it was really. And I don't know if you can give me points back for 12. Number 8 as well. My work is correct, and I just made an error on my calculator.
Yeah.
So, like, if I got those back, then we wouldn't even need to have a conversation about it.
Let's just do this. Just do well on exam 4 and do well on the final, and then we can look at your grade at the end of the semester, and like if it comes down to 1 or 2 questions and some work or something, we'll figure it out.
Okay. Well, I appreciate that.
I can't. The problem is not so much like I want to help. The problem is then I have to think about all the other students in the class, and I get into this. I can't check everybody's work and take. You know what I mean? Like it just gets complicated. But yeah, I mean, if you're doing well in the class and it's coming down to like a couple of questions here or there, and I don't know, I haven't discussed with Samoilenko yet, like if we're going to do some sort of curve or something for the class at the end, so that might help as well. So there may not be any reason to have to worry about it, but I'm saying just on the side, obviously, don't say anything to anybody else. Like if it comes down to a couple of questions and you're working hard and like. Whatever. Yeah, we can massage your grade a little bit and bump it up. I'm not averse to that.
Okay. Well, I appreciate that.
I know that's not exactly like a precise thing to follow, but yeah, just check in with me at the end of the semester and we'll revisit it.
Okay. Well, I'll just do my best to that point. We'll see how it plays out.
Yeah. I mean, you're doing well in the class. I'm sure a lot of students would be stoked to have a 80 something in the class. But yeah, I know. It's tough to get those when it comes down to like 1 question or 2 questions to get an A. It makes it pretty challenging. So, all right. Yeah. Anyway, all right. Anything else?
No, I mean, if we can go with that's good enough for me.
Yeah. All right, cool. Well, yeah, just keep doing well and then we'll revisit and hopefully we can pull out an A for you.
Okay. Well, I appreciate that. Thank you.
You're welcome.
Have a good one.
You too, Tucker.